Okay, so we left off last class session with an analysis of Newman projections for a molecule. Okay, so in this case, we're looking at 2,3-dibromobutane. So what I'm going to do is I'm going to prep a model kit of this. We're going to make a model kit of this. So first and foremost, we are going to focus our attention on the bromine atoms and the relative placement of bromine atoms, okay? So I'm gonna show the model kit on the document camera, and we're gonna look down in our model kit, we're gonna look down the following carbon-carbon bond. We're gonna look down the following carbon-carbon bond. We're looking across the carbon-carbon bond between carbon 1 and carbon 2, okay? So, in terms of what your model kit should look like, it should look a little bit like this. I'll put it on the document cam for your reference. Let's tab over to the document cam. So if we're looking straight down our carbon-carbon bond, you should see something that looks a little bit like this. Okay. Now, once you're looking down your carbon-carbon bond, we're now ready and able to draw out a Newman projection. Okay. So then, let's just start with a basic overview of what's going on here. Looking at the carbon in front, what do we have on our left-hand side? What's on the left? A carbon, hydrogen, or bromine? Carbon, okay? So we're gonna go over to our picture, and looking down our carbon-carbon bond, we're gonna draw out our front carbon, okay? And in this case, we have that on the left-hand side, we have a methyl group, okay? Perfect. Going back to our picture once again, in our model kit, what do we have on the right-hand side? What do we see on the right-hand side in our front carbon? On the right-hand side on our front carbon. Yep, a hydrogen. Okay, so we're just gonna go straight to our kit and we're gonna draw a hydrogen. Perfect. Okay, and then finally, pointing on the bottom is our bromine. So we've handled all of our front substituents. If your exact view does not match mine, that's okay. Just draw what you see looking down the carbon-carbon bond, okay? What we're now going to do is we're going to draw our back substituents. So let's go to our picture once again. So looking at our back substituents, what do we see on top in the back? A bromine, okay? So what we're gonna do is we're gonna move over to our picture and we're gonna draw in the back, let me use a different color for that. In the back, we're gonna draw a bromine pointing up. Perfect. Does that make sense? So once you have your model kit, you just look down your carbon-carbon bond. Let's keep going with this. What do we have on the left-hand side? What substituent do we have on the left-hand side? In the back. So looking in the back, what do we see on the back on the left-hand side? Hydrogen, exactly. So what are we gonna draw? Hydrogen, okay? And then finally on the right-hand side, we have our other methyl group. Okay, so here are the two pictures. Here are the two Newman projections that we have drawn for the following molecule. Both are valid. And a critical aspect that I want us all to pay attention to, looking at our carbon-carbon bond, can we rotate our carbon-carbon bond? Can we physically rotate our carbon-carbon bond and make new relative arrangements of atoms, new conformations? Can I twist this bond? Yes. The carbon-carbon bond is rotatable. And as a result, we can access a range of different conformations that are each represented with a different Newman projection. Does that make sense to everyone? Okay. So If you're curious how to draw a sawhorse notation, so looking at your Newman projection, the only thing that you have to do to get a sawhorse projection is to turn it 90 degrees, so like this. And I'll put this in front of the document camera for everyone to see. So after I've turned it 90 degrees, now I have the typical sawhorse representation. And just like before, we just draw what we see. Does that make sense? How each of these line drawings correspond to a structure? Okay. So what we're now going to do is we're going to focus on drawing Newman projections for another arrangement of atoms, for a new molecule, okay? And we're going to focus on drawing it using our model kit. Now, before we get to drawing out Newman projections, let's talk about the purpose behind Newman projections. So in conformational analysis, we're assessing the relative energy of each conformation. Now, we don't observe perfectly free rotation. There is a barrier to rotation, and some conformers are more stable than others. So some arrangements of atoms are more stable than others in 3D space. Now, atoms and side chains will repel other atoms and side chains. If atoms or side chains are close to each other, they experience a repulsive interaction. If you try to put two things in the exact same spot, they're going to repel. And that's what the model kits are going to help us see. So we call this idea torsional strain. It's that when you rotate a molecule about a bond, there is a repulsion caused when electrons found in different groups pass by each other. So the best way I like to think of it, you can't put two things in the same region of space. If you try to bring two objects too close together, when they pass by each other, there's a repulsive interaction. So if you try to bring two things close together via rotation, eventually they'll be in the same region of space, and this conflict, this repulsion, is destabilizing, torsional strain. Okay, so we're going to look at some of the common Newman projections and common conformations. So what I'm going to do is I'm going to make in my model kit just my typical system that contains only hydrogens. We're just going to look at ethane, the simplest system that we can deal with. So let's make ethane. 2 carbons, 6 hydrogens. And let's visualize ethane, and let's try to see how ethane looks like and how different conformations of ethane have potentially different energies. Okay. So we should have the following model if we've done everything correctly. Now from here, what we're going to do is we're going to visualize first the staggered conformation in our document. So this is the staggered conformation. What do we notice about the relative arrangements of our front hydrogen and our back hydrogen? Are they close together, or are they separated by a large angle? Separated, yep. So the key feature of the staggered configuration is that we have a 60-degree dihedral angle. All of our carbon-hydrogen bonds are as far apart as possible. So we call this angle that separates our substituents, so the angle between the front and back, we call this the dihedral angle. Okay, so 60 degrees is the largest dihedral angle you can generate between your front and back substituents, so we minimize torsional strain. Looking at this structure, are our hydrogens as far apart as we can get them? Are our hydrogens as far apart as we can get them? Yep. And that results in a very low energy system. Now, if we rotate our model, you can generate what's known as the eclipsed conformation. It's the least stable conformation. All the carbon-hydrogen bonds are as close as possible to each other. We have a 0-degree dihedral angle. So let's rotate our model kit now and let's generate the eclipse conformation. So I'm going to rotate my front carbon 60 degrees, and we're going to see the eclipsed conformation. Now, what do we notice about our hydrogens? Are our hydrogens close together or far apart in space? Close together. And do substituents, do atoms or functional groups like to be close together in space? No. So this is highly destabilizing. All we have done is rotated our bond. We went from staggered to eclipsed with just one rotation. Does that make sense to everyone? Okay. Now, let's now take a look at what's known as an energy diagram. So depending on your substituents, we'll have a different gap in energy between the staggered and eclipsed conformations. So in this case, and I really want us to take a moment and let's go through each of our dihedral angles. So let's start off at 0, okay? So at 0 degree dihedral angle, are we staggered or eclipsed? Eclipse. So is this high energy or low energy? High energy. Okay. Let's go over 60 degrees. We go in 60 degree increments. So now are we staggered or eclipsed? Staggered. Staggered. Exactly. Another 60 degrees. What are we at now? Eclipsed. And so forth. Now, this may seem obvious, but since we have all hydrogens, looking at each of our eclipsed interactions, if our substituents were different, would the repulsive interactions be different? Yes. So what we're going to look at now, this is ethane. This is our baseline. We're going to look and see what happens when we add substituents. How does this energy diagram change? One thing that I want you to know, one thing that I want us to take away, if this gap, so if looking at our eclipse conformation, it's approximately 12 kilojoules higher in energy. Now, if we have a total of 3 interactions, 12 over 3 gives us 4. So each of these eclipsed interactions, how much are each of these eclipsing interactions worth in terms of energy? Yeah, about 4 kilojoules. Because how many interactions do we have? 3. 3. Yeah, exactly. Okay. So in this case, all of our staggered and eclipsed conformations are the same. What we're going to look at next are cases where the staggered and eclipsed conformations are different. And when I break you into groups for analyzing a conformation, I'll pass out some additional model kits. Okay. So as we discussed, the repulsion between substituents in the eclipse conformation is about 4 kilojoules for a hydrogen-hydrogen interaction. So this is specific for the hydrogen-hydrogen. If we replace this hydrogen with something else, this eclipsing energy will be a little bit different. Does that make sense so far? So each of these little interactions, as a result of these hydrogens being eclipsed in the same region of space, costs us 4 kilojoules in terms of energy. Okay, let's now look at a more complicated example. Let's look at propane. So what we're going to do for propane, is we're going to replace one of our hydrogens with a methyl group, with a carbon. And to really help us visualize the methyl group, to that carbon that we added, we're going to put 3 hydrogens on that. Okay, so propane should look something like this when you're done. 3 carbons, 8 hydrogens. We're going to focus and look down one of our carbon-carbon bonds. And I'm going to put this on the document cam for all of us to see. I'm going to put this on the document cam for all of us to see. So, if you've assembled propane correctly, we're going to look down one of our carbon-carbon bonds, and you should see something that looks very similar to this. You always want to be staring down one of your carbon-carbon bonds. And I'd like you to put the methyl group in front, so that way we're all on the same page. Is everyone there with their structure? Is everyone, and if not, can you see the structure presented on the front document cam? We're going to be looking at different conformations of propane and then analyzing their energies. Okay, so that's what we're doing now. So first and foremost, we're going to look at the eclipsed propane. We're going to look at the eclipsed propane. As we've discussed, each of our hydrogen-hydrogen interactions, each of our hydrogen-hydrogen eclipsed interactions costs us how much energy? A hydrogen-hydrogen eclipsed, 4 kilojoules. Now, the new interaction that we're going to look at is a methyl hydrogen eclipsed interaction. And this interaction costs us approximately 6 kilojoules per mole. So it's a higher energy eclipsing interaction. And let's see why that is. Let's see why that is. So if we draw the eclipsed conformation, if we adjust our model to reveal the eclipsed conformation, they're all 0-degree dihedral angle. All of our substituents are aligned. Now, let's take a look at what in 3D space is our methyl group, just in 3D space, is our methyl group bumping into? Is it closer to our hydrogen? Would we expect a greater steric interaction if these groups are bumping? Yeah. So as a result, would we expect this to be a higher energy interaction? Yes. Okay. Perfect. Now, the eclipsed conformation is higher in energy as a methyl hydrogen interaction is highly destabilized. And you really want to be familiar with these interaction energies as we'll be using them in later chapters. Okay. Now, this situation gets more complex when we have larger alkanes. So what we're going to do is we're going to make butane. So just like always, we're going to take one of our hydrogens, off, and we're going to replace it with a carbon. And to that carbon, let's put a total of 3 hydrogens. So let's work on building butane, and I'm going to pass out the components to build butane to a few groups in the class. So make sure you build up your butane model, and then we'll discuss in about 2 minutes. I'm going to pass out some model components. Let's put together butane, and then we'll discuss in a moment. Okay, so I have butane prepared. If you've done everything correctly for butane, you should see 4 carbons with a total of 10 hydrogens. So this is what butane looks like. We're going to look down the middle 2 carbons. We're going to take the middle 2 carbons and we're going to look down them. So I'm going to put this on the document cam so that way everyone can visualize it, and then we'll discuss from there. Okay, so this is what staggered butane looks like. If you're looking at the staggered conformation down the middle carbon-carbon bond. Is everyone seeing what I see? So I'm going to take my butane molecule, I'm going to rotate it 90 degrees, I'm going to look down the carbon-carbon bond in the middle of butane. And you should, if you're looking at the view in the same way I am, it should look a little bit like what's shown on the document camera. Everyone seeing what I'm seeing? Okay. Now we can do some analysis on butane conformations. What I want you to do is to generate the eclipsed conformation. And I want you to rotate it so the hydrogen is aligned with the methyl group in back. This is the first eclipsed conformation we're going to look at today. Now, what do we see in this conformation? So looking at it, do we have 2 hydrogen methyl interactions? Do we see 2 hydrogen and methyl interactions? 2 cases where they're bumping together? Yes. Okay. Now, from this information, from this idea that we've seen two hydrogen-methyl interactions. Each of these hydrogen-methyl interactions are 6 kilojoules apiece. The hydrogen-hydrogen interaction is 4 kilojoules, okay? But, and this is really important in butane, is there a potentially more disruptive eclipse conformation? Is there a conformation that's even higher in energy? Can we bring two really large groups closer to each other? Let's try rotating our molecule. Let's try rotating our carbon-carbon bond. And let's think, we have these giant methyls, right? So what would be an even higher energy eclipse conformation if these methyls were eclipsed? So let's rotate our molecule and let's see what happens if our methyl groups are directly eclipsed. Now, you can even see this looking at the model clip. Are these methyl groups almost right on top of each other? Are they bumping into each other? Yeah. We can see this clear steric interaction, this clear torsional interaction. And as a result, would we expect this to be higher or lower in energy? Higher. Okay. So then, let's take a look. So we've discussed the first eclipsed conformation of butane, right? We've already added up all the energies, and we said this, we have an energetic difference of about 14 kilojoules per mole. Now, the second higher energy eclipsed conformation involves with our methyl groups eclipsed. And the key thing I want you to take away is that our methyl-methyl eclipsing interaction is approximately 11 kilojoules. So it's almost double the methyl hydrogen eclipsing interaction. And that makes sense. Do the methyl groups take up more space? Yeah. Now, one thing I want us to focus on, is our eclipsed conformations are not just different in energy. Our staggered conformations also exhibit a difference in energy. So what I want us to do as we move through the different bond rotations is I'd like you to start with a structure where our two methyl groups are completely opposite to each other. So I'd like you to generate the following Newman projection, because we're going to start from that and let's try to comment on its energy. So looking at this Newman projection, are our methyl groups as far as possible from each other? Are our methyl groups as separated as possible from each other? Yes. Now, as a result, would you expect the system to be high or low in energy? Low. Yeah, we've separated our methyl groups. So we call this conformation where our two largest substituents are farthest apart. We call this the staggered conformation. So this is the lowest energy conformation. So we'll assign it the value of 0 in relative terms. Now, let's look and let's see what happens when we generate our first eclipse conformation. So we go 60 degrees to the right, and we have our first eclipse conformation. Now, looking at this picture, what kind of eclipsing interactions do we have? What two things are bumping into each other? Hydrogen and a methyl. So that's destabilizing, but not super destabilizing. Okay? And we've seen that in this picture here. So we have our hydrogen methyl interactions, and they cost us about 6 kilojoules per mole. Now, let's look at our second staggered-like conformation, and let's notice something that's a little bit intriguing. So we've generated, by rotating another 60 degrees, a staggered conformation, a staggered-like conformation, but this is not the same energy as your typical staggered conformation. Does anyone notice something odd in this picture? What groups are pretty close together? The methyl groups. So even though they're separated by 60 degrees, are they still close together? Yes. So we call this interaction where we have two large groups separated by a 60 degree dihedral angle. We call this a Gauche conformation and a Gauche interaction. And a methyl, a CH3 Gauche interaction costs us about 3 kilojoules per mole. One moment. Well, we can round it to about 4 kilojoules per mole. So it's a destabilizing interaction, but it's not a direct eclipsing interaction. This is two substituents very close together in space that repel each other, as a result of sterics. These methyl groups take up space, and this repulsive interaction results in a higher energy system. Does that make sense? Can everyone see how these two methyl groups, even though they aren't eclipsed, they're close enough in space for them to interact and repel each other and undergo steric repulsion, steric destabilization. These methyl groups are in the same region of space, and so they repel each other. They're not eclipsed, they're still staggered. There's a separation in their angle. They aren't as close together, but it's still a destabilizing interaction. Does that make sense? Okay. Now, the reason why I want you to know this energy is this butane, this methyl-methyl gauche interaction pops up a ton in different systems. So anytime you have two substituents that take up space, that are close together in space, they'll repel each other via steric repulsion. Okay. Now, finally, we can move to our eclipsed conformation. We can move to our eclipsed conformation. And as we discussed, when these methyl groups are directly eclipsed, is this the highest or lowest energy conformation? Highest. Why? Are these two methyl groups almost bumping into each other? Are they bumping into each other in space? Yes. So then this is the highest energy interaction. Now, the key takeaways from this discussion, the key takeaways that we observed from playing with our model kit is that this Gauche conformation is higher in energy as the result of steric strain. So this is known as steric strain. This is this idea that substituents take up space, and if two bulky groups are in the same region of space, they're going to repel and destabilize each other. Now, with that said, we're going to apply the same conformational analysis, quite simply making a model and looking at how the groups interact in space to assess the energy of new systems. So let's try and do some conformational analysis on butane. Let's make a picture of the energy diagram for butane. Now, what I want you to do in each of these cases is I want you to, with your model kit, make each of these conformations. I want you to generate each of these conformations with your model kit, and I want you to add up all of the interactions and try to match the energetics of each of these interactions with the total energy of your system. And I'd like you to explain why this first eclipse conformation is lower in energy than this middle eclipse conformation. And in this time, I'll be passing out, how many people need a model kit for today? Okay, so I'll pass out 2 sets to each group. So work on this for about 3 minutes. Try to highlight each of the interactions and look at and try to explain the relative energies of each of these conformations. And we'll discuss in about 3 minutes. Here you go. Here's one for each. I have the kit for your break here. You have the pieces needed to visualize it. So, what do you see? So then are they completely staggered? This is far apart. So, taking a look, now everyone has their model kit, and we've been playing with our model kit for a while. So let's start off with our first our first staggered conformation that we call the anti-conformation. So looking at the anti-conformation, are our methyl groups as far from each other as possible? Yes, they're separated by a 180-degree angle. So would we expect this to be the highest or lowest energy? Lowest. We've minimized our eclipsing interactions. So we have a 180-degree angle separating our methyl groups. So we call this the anti-conformation. Now let's rotate 60 degrees. Let's rotate 60 degrees. Ah, yes. So from the side, it should look like something like this. And from the front, it looks like something like this. Now, what kind of interactions do we have in this eclipse system? What kind of eclipsing interactions do we have? Between what two substituents? Hydrogen and methyl. And how many of these eclipsing interactions do we have? 2 hydrogen and methyl interactions. Exactly. So we have a hydrogen methyl interaction that costs us 6, a hydrogen methyl that costs us 6, and a hydrogen that costs us 4, leading us to a total of 16. So this is one of our first eclipsed conformations. Now, if we rotate another 60 degrees, we end up with a conformation that is not quite anti. What do we call this conformation when our substituents that are bulky are separated by 60 degrees? Gauche. And what kind of interaction? What do we call this interaction? The methyls are close in space, but they aren't eclipsed. They're close in space, they're repelling each other, but they aren't eclipsed. What type of interaction do we call that? Steric, exactly. We have groups that take up space being pushed into the same region of space. So our 2 methyl carbons are relatively close to each other, but they're separated by 60 degrees. Okay, so this gauche interaction is about 4 kilojoules. And that's why our gauche conformation is slightly higher in energy. Now we're going to rotate another 60 degrees. And you should end up with the following completely eclipsed conformation. So we rotate it 60 degrees. And you should end up with a conformation where both of your methyl groups are completely eclipsed. Yes. So So gauche represents the conformation. The interaction between the methyl groups is a steric interaction. So people sometimes call this kind of steric interaction a gauche interaction. But gauche refers to the arrangement of atoms in a Newman projection, while the steric interaction refers to the exact interaction between your substituents. Does that make sense? Perfect. So in the case where both of our methyl groups are now completely eclipsed, would we expect this to be high or low in energy? High. How much energy does this methyl-methyl interaction, where our two methyl carbons and our methyl hydrogens are bumping into each other? How much energy does that cost? 11. Yep. So this is a very high energy interaction that costs us about 11 kilojoules. Each of these hydrogen-hydrogen eclipsing interactions costs us 4 kilojoules, leading us to have a total relative energy of 19 kilojoules per mole. So I like to call this the eclipsed, where we have our methyl groups completely eclipsed. So I label this eclipsed methyl-methyl. Okay, now if we keep going, we'll go through the exact same set of conformations except in reverse. So if we rotate another 60 degrees, what do we call a conformation where our bulky substituents are separated by 60-degree dihedral angles? What conformation? What do we call this conformation? Gauche. So we go back through our gauche conformation. And as we discussed, because we have the same methyl-methyl interaction in the second gauche conformation, would we expect it to be the same or different energy? Same. So that's why it's also has a relative energy of 3.8 kilojoules per mole relative to the anti-configuration. Does this make sense, the logic used to fill in these energy diagrams and how we get each of these values in these energy diagrams? We look at our interactions and we add up the energetic penalty of each of these interactions. Does that make sense? And a beautiful thing, thankfully, in this example, we only have 2 substituents. If you have more than 2, you'll have to go through all the way from 180 degrees to 180 degrees. The reason being is that if you have multiple substituents, the exact nature of these interactions may change. We only have 2 methyl groups in this case. In other examples, you could have eclipsing interactions between a range of different substituents. Okay? So you should be able to, just like we did together, look at a molecule and draw out the energy of each conformation. Does that make sense, what's expected of you for this chapter? Okay, let's now try another example. Now, I have this table for you to reference with regards to the common interactions I want you to know. So if you ever want to reference any of our hydrogen-hydrogen, methyl-hydrogen, and methyl-methyl eclipsing interactions, all of these are provided to you. On an exam, I want you to know all of these interactions by heart. If I give you a table of interaction energies, I'll tell you which ones I expect you to memorize. This is one that you should be familiar with as it pops up on the ACS exam. Okay? So let's now put this into practice. We're given a molecule. We're given a molecule shown here. And our goal is to identify the lowest and highest energy conformation across the carbon-3, carbon-4 bond. So using numbering, this is carbon-3, this is carbon-4. Whenever you're given a numbering scheme, it is following the numbering scheme from nomenclature. Okay? So the first step to approaching any problem is making a model kit. If you make a model kit, you'll save yourself some time. So what I'm going to do to help everyone along with this process is I'm going to pass out to each of the groups that I handed a model kit an additional carbon so that they can complete their model kit. I'd like us all to make this model, and then we'll start our discussion in about a minute and a half. Yeah, we're only looking across those 2 carbons. Across carbon 3 and 4. So here's a carbon to that. And here's a carbon to that. Okay, so everyone's noticed that this molecule is a little bit more unwieldy. That's okay. So we're going to look, so here is our long chain molecule. So we have our ethyl group right here. We have our methyl group right here. And we have our propyl group right here. We're going to look down carbon 3, which is this carbon right here that I have in my hand. We're going to look down the carbon 3, carbon 4 bond. So your end view should be looking down, directly down this carbon 4, carbon 3 bond. I'll project this on the document camera so everyone can see. So your view at the end should look a little bit like this, just as a starting point. So we're looking down our carbon 3, carbon 4 bond. And we have a lot going on here. We have a lot. Oh, one moment. Let me just check really quickly.
It's supposed to be 7.
Let me see. So here's our ethyl, our methyl. Okay, methyl group's attached. And we have a propyl. Oh, okay, perfect. So in this case, carbon 3 should be this carbon right here, the one directly attached to the methyl group. We're going to look down carbon 3, carbon 4. And we're going to end up with the following view, if everything's gone correctly. Does your view match mine, looking down carbon 3, carbon 4? You're looking down the carbon that the methyl group is directly attached to. Does this look familiar to what you're seeing? Is everyone looking down this structure with the same view? Let's just rehash it one more time. So here's our molecule. Here's our ethyl group. Here's our methyl group. I grab the carbon attached to the methyl group and I turn it so I'm now looking down the carbon-carbon bond. Is everyone okay so far? So I have my methyl group, I have my ethyl group, I turn it over and I look down the carbon-carbon bond. Is everyone okay? Can I get a thumbs up if you can see it okay? Okay, perfect. So now let's look at in our model kit and we're gonna play a game. We're gonna try to rotate this molecule to minimize our interactions. So what are our biggest groups? What are the biggest groups? What things have the most carbon? What things are taking up the most space? So looking at our front, is the methyl, hydrogen, or ethyl group? What's the bulkiest thing? What would have the greatest steric effect? What takes up the most space? What was that? The methyl or the ethyl? The one with 1 carbon or the one with 2? 2. And the way you can see this is this ethyl group can just swing around and rotate, and as a result, it eats up a lot more space, has a greater steric repulsive effect. Now, looking at the back, which group is the largest? These 2 hydrogens or this propyl group? What takes up more space? Just looking at it. What's taking up more space in your view? The propyl group or the 2 hydrogens? The propyl, exactly. Okay, so we have our propyl group and our ethyl group, and our mission in life, if we want the lowest energy conformation, should we have the propyl and ethyl group be as close together or as far apart as possible? We want the lowest energy. Far apart. Okay, so what I'm going to do is I'm going to set it up so there's 180 degrees between my propyl group and my ethyl group. Okay, so we do have some gauche interactions, but have we minimized interactions between the propyl and the ethyl group? Have we separated our propyl and ethyl group? Yes. So then, if we want to draw this conformation, do we now have a picture that we're just going to write down on our piece of paper? Do we now have a picture that we can now draw on our piece of paper in Newman projector form? Yes. So let's do just that. Okay. So looking down our carbon-3, carbon-4 bond. So I have carbon-3. So carbon-3. Let's draw a picture now. So what substituent is on the left on our front carbon? What substituent is on the left? Methyl group. Okay, so I'm just going to draw on the left a methyl group. Okay, let's keep going with this. What substituent do we see on the right? In the front carbon, what do we see attached to the front carbon on the right? Hydrogen, exactly. So all we're going to do is we're going to draw a hydrogen. Finally, what is pointing down on our front carbon? What group is that? 2 carbons, what do we call that? Ethyl. So let's draw that out. So now we have our ethyl group. Okay, perfect. So we've drawn a picture of our front substituents in our Newman projection, looking down carbon-3 across the carbon-3, carbon-4 bond. What we're now going to do is we're going to draw our back substituents. So looking at our back substituents, what's pointing up in the back? Propyl. Okay, so we're going to draw our propyl. 1, 2, 3. Yep, so that's our propyl. And then what is pointing down and to the left? What's in the back? It's sort of behind the methyl. It's hard to see. Hydrogen. Yep, so we'll draw our 2 hydrogens. One on the left and the other on the right. Okay, so let's summarize our interactions. So we do have a gauche interaction here. Would we expect this gauche interaction to be higher or lower in energy than our typical methyl-methyl interaction? Are the substituents bigger or smaller? Do they take up more or less space? More space, right? If we look at this propyl group is just obnoxious. It takes up a ton of space. It has 3 carbons. It's bumping into our methyl group and taking up a lot more space. These 2 substituents are being pushed into the same region of space. So is this a higher or lower energy interaction than the typical methyl-methyl interaction? Higher, yep. Okay, so this is a gauche interaction, and we'd expect this interaction to be greater than our typical 4 kilojoules per mole. Okay, does this logic make sense to everyone? How we arrived at the lowest energy conformation? We drew out and we played with our model kit and we tried to place our largest groups as far apart from each other as possible, the farthest dihedral angle separation. Now, we can entertain other gauche conformations. So let's rotate our model kit. Let's rotate our kit to generate another potential gauche interaction. Let's draw out a potential second gauche interaction, and let's see why this interaction is higher in energy. So we're still looking down carbon-3, down the carbon-3, carbon-4 bond. So this is another potential gauche conformation. Would someone care to explain why this gauche conformation that I've drawn right here, this gauche conformation that I've indicated right here, why is this gauche conformation higher in energy? What's the main problem with this gauche conformation? You're on the right track. So we have our methyl group. Is our methyl group bumping into our propyl group in the back? Yes. Is our ethyl group also bumping into the propyl group? Is our ethyl group also close in space to the propyl group? Is it also gauche? Okay, so let's unpack this. Gauche interactions occur when there's a 60-degree separation, right? So the 2 things that we have that are 60 degrees separated in terms of dihedral angle are our methyl group and our ethyl group, right? So do we have more gauche interactions in this following conformation? Will we have more or less gauche conformation? Gauche interactions? More, right? Because we have more substituents in closer regions of space. So let's draw that out just so we can see this pictorially. So drawing out our front substituents for our alternative idea. So in our front substituent, we have our methyl group, we have an ethyl group, and then on the bottom we have a hydrogen. Now in the back, we have our propyl group in the same position, and we have our two hydrogens. So looking at the conformation, looking at this conformation and looking at our interactions, does everyone see now why we have more destabilizing steric interactions? Because instead of just having a methyl group and a propyl group, we still have our methyl-propyl interaction. We still have our methyl-propyl interaction. But what new interaction, what new destabilizing interaction have we introduced? Yeah, it's a gauche conformation. We have a steric interaction between what two substituents? The propyl group and the ethyl group. So we have an ethyl-propyl interaction. And it's a steric interaction as a result of a gauche conformation. Yes?
Would having the propyl group on the C4 carbon make this a different molecule?
Propyl group on the C4 carbon? Yes. Yes.
So were we looking at this molecule, or because this one that we're looking at right now has 8 carbons, right?
1, 2, 3, 4, 5, 6, 7.
Is it the back?
8.
Carbon?
Yep.
So,
1, 2, 3, 4. Let's see. Ah, sorry, this should be an ethyl. Yep, you're completely correct. This is an ethyl-ethyl. So in the following conformation, we have a greater number of steric interactions. So that's why this conformation, although it is gauche, it's higher in energy. Let's draw, are there any other potential conformations that we can draw that we think would be low in energy? Are there any other gauche conformations that we can draw? So we have one where we have a methyl-ethyl interaction. We have one where we have an ethyl-ethyl and a methyl-ethyl interaction. We've established that's higher in energy. Are there any other gauche conformations we can draw? Are there any other ways that we can rotate this carbon-carbon bond? Well, let's try. Let's try and see. So, as we rotate and we look at a potential anti-conformation, we have, in this case, we have an anti-arrangement comparing our ethyl group, get rid of that carbon, comparing our ethyl group to the methyl group. Now, although we have our ethyl group and our methyl group separated by the largest dihedral angle, what substituents are now gauche? What substituents are now separated by a 60-degree dihedral angle and are close in space? The two ethyls, exactly. Does everyone see how these two ethyls are close to each other in space? They're gauche to each other. Does that make sense from that view? Let's now draw the Newman projection and let's assess the energies of these interactions. So in this case, we have our ethyl on the right, our hydrogen on the left, and our methyl pointing down. On the back, we still have our ethyl group and we have our two hydrogens. Okay, so looking at this picture, do we have a steric interaction, and between what substituents? So what two substituents are close together in space, separated by a 60-degree angle? Yep, the two ethyls right here. So we have an ethyl-ethyl steric interaction. Now, let's do some comparison now. If we compare our ethyl-ethyl interaction to a methyl-ethyl interaction, what would you expect to be lower in energy? What is smaller, a methyl group or an ethyl group? What is smaller? The methyl, exactly. So then, would you expect this methyl steric interaction to be lower or higher in energy? Lower, right. So this ethyl-ethyl steric interaction is higher in energy. Okay, perfect. So we're able to compare the steric bulk of our substituents and decide what steric interaction has a greater penalty. Does that make sense? Okay, so of these gauche and anti-like conformations, which of these three conformations is lowest in energy? The structure on the left, the conformation on the middle, or the conformation on the right? What's lowest in energy? The right, exactly. So let's put a box around this. And the key feature of this structure, is that our large substituents are anti. What is the dihedral angle? What is the angle separating our bulky groups? 180, exactly. So in general, if I ask you to draw the lowest energy conformation, you're going to want to put your largest substituents how far apart? How many degrees apart? 180, exactly. Does that make sense? Okay, now let's try and play a game. What is always going to be the highest energy conformation? What is always going to be the highest energy conformation? What do I want to do? What do I want to bring as close to each other as possible? What do I want to eclipse? The largest groups or the smallest groups? Largest, okay? So I have an ethyl here, I have an ethyl here, so I'm just going to line them up. So you want your two ethyls as close to each other as possible, completely eclipsed. So you want your two bulky substituents completely eclipsed. Yes?
So what's the difference of a Steric interaction and eclipse?
So an eclipsing interaction is the dihedral angle is 0 between them. Well, a steric interaction, the two molecules are separated by a dihedral angle. They're separated in space, but because the molecules and because those portions, those substituents, take up space, even though they're separate, because they spread out and take out space, they bump into each other. So an eclipsing interaction, the substituents are manually brought into the same region of space. They're 0 degree dihedral angle, they're almost right on top of each other in terms of space. They're torsionally very close together. Well, for sterics, the substituents are separated in space, but the substituents are so large that their size causes them to bump into each other. The substituents take up so much space that even though they're separated by a 60-degree angle, they're still able to interact and destabilize. Does that make sense? Okay. The other difference is that an eclipsing interaction is it's somewhat temporary in nature. It's brought about as you rotate your bonds, the substituents become eclipsed, and then they rotate further and they're no longer eclipsed. A steric interaction cannot be fully removed via rotation. The substituents still take up space, no matter how you rotate. Does that make sense? Perfect. Okay, so then, if we had to play a game, if we had to pick the worst possible conformation, the highest energy conformation, why am I eclipsing my ethyls over eclipsing my methyl in the ethyl? What substituents are more bulky? What substituents have a greater steric effect? Ethyl, because the ethyl takes up more space. Okay, so let's draw out that Newman projection. Let's draw out that Newman projection now. So in the front, we have our ethyl, we have our methyl, and we have a hydrogen. In the back, we have our poor ethyl group, a hydrogen, and a hydrogen. So in terms of our interactions, let's write them out and quantify them. So here we have an ethyl-ethyl And what do we call this interaction when there's 0-degree dihedral angle? They're right on top of each other in terms of the dihedral angle. Eclipsed. So this is an ethyl-ethyl eclipsed interaction. We also have a methyl hydrogen eclipsed interaction, which costs us about 6 kilojoules, and we have a HH eclipsed interaction that costs us about 4 kilojoules. If we had to take a guess, considering a methyl-methyl was around 11 kilojoules, what would you expect an ethyl-ethyl to be? About. Greater than or less than 11? Greater. So let's just say, for the sake of argument, it's around 16 to 20 kilojoules. Just to signify it's a much more destabilizing interaction. Now, let's compare this to our other eclipsed interaction. Let's compare this to our other eclipsed interactions. So, the next possible eclipsed interaction, we have a methyl-ethyl eclipsed interaction. So let's assess its energy now, and let's look at the Newman projection to visualize why this conformation is lower in energy, or not as high in energy. So, in our next possible conformation, we have our methyl group pointing up, our ethyl group pointing to the side, and our hydrogen pointing to the right. The back stays completely the same. We have our ethyl group, and we have our 2 hydrogens. Okay, so in terms of our interactions, let's highlight each of our interactions once again. So up here, what 2 substituents are bumping into each other? What 2 substituents are completely eclipsed? This is our methyl. So it'd be a methyl and an ethyl. Okay, so this is a methyl-ethyl interaction. Just one moment. And this is an eclipsing interaction. Okay, and about how much energy would we expect this to cost? If we assigned an ethyl-ethyl to be about 16 to 20, should this methyl-ethyl be a higher or lower energy eclipsing interaction? Lower. So let's say about 12 to 14 kilojoules. Well, like 13 to 14 maybe. Just to get into this idea that the substituents take up less space, they have a lower steric penalty, and as a result, this eclipsing interaction is not as destabilizing. It doesn't increase our energy as much. Additionally, we have an eclipsing interaction between an ethyl and a hydrogen eclipsing interaction. Now, this is something that's important to consider. Would this be more or less of an energetic penalty than a methyl hydrogen interaction? So if a methyl hydrogen interaction is around 6 kilojoules, what would we assign for our ethyl hydrogen interaction? Yeah, 7 to 8. It's greater because the ethyl group takes up more space. And then finally, we have a hydrogen-hydrogen interaction that costs us 4 kilojoules. Does that make sense? Does everyone see why this first eclipse conformation that we drew is the highest in energy? Finally, let's go through and let's draw our last possible eclipsed conformation. So we have one last option. We can have all of our substituents eclipsing a hydrogen. Would you expect this to be the lowest or highest energy eclipse conformation? Lowest, right? Because are we placing our bulky groups next to hydrogens instead of other bulky groups? Yeah. So then, let's do another energetic analysis. I really want you to get in the habit of going from your Newman projection to assess the relative energies of these interactions. Okay, so in front we have our hydrogen, our ethyl group, and a methyl group. In the back, we have an ethyl group, a hydrogen on the left, and a hydrogen on the right. Let's now tally through all of our interactions and let's assign some energies. right? So we have up here, we have a methyl hydrogen eclipsed interaction, and we assign this as about 6 kilojoules from our table, right? We also have an ethyl hydrogen eclipsed interaction. And what do we assign for our ethyl hydrogen eclipsed interaction? About 7 to 8. And then finally, we have a methyl hydrogen eclipsed interaction. And what do we assign to that? 6. Yeah, so it's about 6. So then, can we theoretically plot each of these conformations in terms of their energy? Can we add up each of these interaction energies and make a plot just like we looked at earlier in this chapter? Yeah. So then, we've established that this first conformation that we drew, where our largest substituents are completely eclipsed, is the highest energy conformation. Does that make sense? So let's put a box around that. The reason why I went through all of these steps in detail is so that way you can process the energy of each of your conformations and you're comfortable drawing Newman projections for each of the conformations. Do the model kits help in this regard? Visualizing how the substituents are arranged and seeing why steric interactions are destabilizing? Your two groups are brought into the same region of space and they repel each other. Now, we did this first example together. What I want you to do now is to take the lessons from this first example. You don't have to draw everything. You don't have to draw it in as much detail as I did. But I want you to take the lessons from this example, that the highest energy conformation has the bulky substituent staggered and the lowest, bulky substituents eclipsed, and the lowest energy conformation has the bulky substituents completely anti from each other. Now, let's take a look, and what I want you to do is to take a look at the following system. I want you to take a look at the following system. And I'd like you to look at the conformations, this time across the carbon 2 and carbon 3 bond, as this is carbon 2 and this is carbon 3. So I'd like you to draw out Newman projections and identify the lowest and highest energy conformation. And if we're making a model kit, if we're making a model of this structure, your model should look something like this if you're starting out. 5 carbons, a methyl on carbon 2, and you're looking down carbon 2. Does that make sense? It should look a little bit like this. I'll walk around and check to see how everyone's doing, and then we'll come together to discuss in a few minutes. I used this when I was studying. It's actually no problem at all to use. It's just a little bit of a hassle, but nothing obvious. Yes. So anytime you're looking down a bond, you want to make sure that these are sp2, so that way you can make a combination. Here you go. And now Let's round up this one. This end of this one. Everything going okay? So what would be the problems like energy combination? Yeah, exactly right. Exactly right. So I'm gonna draw it. So it's I see is so looking down carbon. Looking down carbon 2 to carbon 3, is that the highest energy or lowest energy? And why is that? Yeah, the two methyls are completely eclipsed. Does that make sense? So now all you have to do is look down this carbon-carbon bond and draw the Newman projection. Draw all the groups in front exactly as you see it. Draw them back. Does that make sense? And sorry again about the. Yes, exactly. Yes, exactly.
Yeah, so like it tells you how
So looking at
this carbon, so you just want like the carbon two right in front of you, and then you want right behind it where you can't see it. Like this. Yes. And then you rotate.
You draw the front first. Yes.
Okay, I just want to make sure I'm doing them.
Okay.
Yeah, this correct. Okay, so you see
Yeah.
the bond is this one, and when it's correct, you're down like
Keep it
this.
the same,
So
and then
then,
move
is
the
this
back
diagram
one
correct?
60 degrees each time.
So I have.
Oh, I see. I got it. Got it.
Yep.
So the methyl,
Yep. Is
another
This,
methyl,
and then the
hydrogen,
back.
and the two methyls are one together.
Yeah.
Okay, okay, now I get it.
Does that make sense? You're able to visualize the kind of thing also. Or where's your goals?
Two that I have so far. This one's probably the highest.
And then we're gonna do this one.
Yeah, it's between the two.
Good, so- How's it going? Yep, yeah, you're right.
When I rotate,
Yes.
when I rotate,
Yes. You can turn the front.
I'm rotating too, right? Yep. I really thought it was gonna be like last year. I didn't. But when I was watching, I was like.
And try testing that, because any other way to do a regular situation is always. Yeah, exactly right. Everything going okay?
I'm not sure how to quite look at it.
So carbon 2 is right here. So you look down this carbon 2, carbon 3 bond. Now what you're going to do is you're going to rotate your molecule and you're going to try to minimize interactions where your groups are directly aligned and you want them as far apart from each other as possible.
Oh,
So you're looking down this bond.
yeah, like this, right? And then
Yes,
right. And a good question. What do you think I can talk to you after?
yes, yes. Sorry, sorry about that.
So, say carbon 2 is like the proton stuff, and that's if you like connect to here's like the two streets, you know?
Yes. Yep. Oh, but then, so if you draw the two methyls from this card, one on one, how does it look?
the front.
Oh, I drew it. That's what you're talking
Let's see. So you have, yep, so this is carbon 2, carbon 3. Yep. And your goal is to try to separate and minimize your eclipsing interactions.
Okay, wait, and then, so we have another question. Difference. So if I'm looking at these, it's eclipsing interaction.
Yep.
Or like, what's taking this down considered?
So like.
Oh.
Yep.
So like if there's a 0 degree, I'm gonna put that on.
So, oh, yes.
So this is what that helps with like.
So let's take a look at the following system. And this is a good example. I saw a lot of the good practices needed to assess the relative energies of your system. So looking down our carbon 2 to carbon 3 bond. So if you want to just think of it as if we're rotating this entire structure 90 degrees. So looking down their carbon 2 to carbon 3 bond, we should end up with something that looks a little bit like this. Okay, so we're looking down the carbon 2, carbon 3 bond, and let's start with the highest energy conformation first. What interaction is most destabilizing? A methyl-methyl or a methyl-hydrogen interaction? Methyl-methyl. Okay, so I'm going to turn my molecule, turn my carbon-carbon bond so that the two methyl groups are directly eclipsed. So is this the highest energy conformation that we can make? Yes. So now all we have to do is draw out the Newman projection. So in the front, let's look at our picture. Let's look at our model. What substituent is on the left in the front? The methyl. Okay. What substituent is on the right in the front? Right in the front. What substituent is on the right in the front? Hydrogen. Yep. And then finally, what substituent is on the bottom in the front? A methyl. Yep. Okay, perfect. What? Oh, yep. So we've completed our front picture so far. Let's now draw the back substituents. Let's now draw all the substituents in the back. So what substituents are in the back? What's in the right on the back? The methyl, okay. So we have our methyl on the right, and our two hydrogens occupy the remaining positions. So if you're doing energetic analysis here, we have a methyl-methyl eclipsed. And how much does a methyl-methyl eclipse interaction cost? About 11. 6 is for a methyl hydrogen. So let's talk about that actually. So down here, we have a methyl hydrogen interaction, and it's an eclipsed interaction, and it costs us about 6 kilojoules. Finally, we have a hydrogen-hydrogen eclipsed interaction, and that costs us how much energy? 4. Okay. So this is as high energy that we can get because we've maximized our eclipsing interactions between our bulky substituents. Does that make sense? Okay. Now, let's play a game and let's try to figure out the lowest energy conformation. So what groups do I want as far from each other as possible? The methyls. So let's take my methyls. Let's take my two methyls and let's separate them. What's the farthest angle we can separate them by? 180. So I'm going to take my two methyls and I'm going to separate them by 180 degrees. This is known as the anti-conformation. Okay. With that established, now all we have to do is draw a picture. Okay. So in front, what do we have on the left? What do we have on the left in our front? Hydrogen. Okay. So following similar logic, so we're going to draw our hydrogen on the left. Oops, one moment. What substituent, what substituent do we have on the right? Methyl. And what do we have on the bottom? Methyl. Okay, so let's draw those out. So we have a methyl on the right and a methyl on the bottom. Let's now draw our back substituent. So in the back, what is pointing on top? What is pointing up? Methyl, okay. Okay, and our two hydrogens occupy the other staggered positions. Okay, now taking a look, let's assess each of our interactions. So first and foremost, what appreciable gauche interactions do we have? What gauche interactions or what steric interactions are we dealing with here? Do we have bulky substituents separated by 60 degrees but still close together in space? Yep, so we have a methyl-methyl interaction. So let's draw that out. So we have a methyl-methyl steric interaction. And how much energy does that cost? How much does the methyl-methyl steric interaction cost? About 4. If you want to be exact, it's about 3.8 kilojoules that we can round to 4. So is this as low energy of a system that we can go? Is this the lowest energy system we can make? Is there any way to get 2 methyls as far apart as we can? No matter how we rotate it, are we always going to end up with a methyl next to another methyl? Yes. So then, this is the lowest energy conformation. This is our lowest energy, and this completely eclipsed conformation is our highest energy. Does that make sense? Okay. So what I want you to be able to do is I want you to practice a little bit on some of the pre-lecture assignments in identifying the lowest and highest energy conformation. There are additional problems in your book. And I really just want you to get familiar with taking a model kit and manipulating it in order to see how substituents interact in space. We'll be doing a lot more work with model kit next time. This lecture is primarily an introduction, just to get everyone used to breaking out the model kit and using it productively. So we'll continue this lecture next session with a few more problems.